In this section, we're going to finish 5.3 with de Moivre's theorem. And the first thing we're going to talk about is something we hit on last time, which is the idea of magnitude. And magnitude is simply the distance from whatever point you're at in the complex plane back to the origin. So if your complex number is z equals x plus yi, you can actually find this in very much the same way that you would if you were finding the value r with polar coordinates. And you'll notice that z is actually the square root of x squared plus y squared. And that should feel a lot like the Pythagorean theorem because that's what it is. It finds distance, or the distance formula. And sometimes this is called the absolute value of z, and you can see the notation has that same the same absolute value kind of bars to it, so that's kind of the interchange for language, but the actual real notation is actually this is the magnitude of z. The rectangular or Cartesian form is the z equals x plus yi that we've been using, and it's the coordinate xy in the rectangular plane, the Cartesian plane. But it's not the only way we can represent the numbers. We can also represent them in polar form, as we've seen in earlier parts of this chapter 5. And the polar coordinates are r theta, and you'll notice the same x equals and y equals formulas we had from before. X is r cosine theta, y is r sine theta. So my z value that can be written as x plus yi in rectangular form, we can substitute the x for r cosine theta. We can substitute the y as r sine theta. And then, as you notice, each of those pieces have an r in it. We could factor the r out in front for another form of the polar equation, or polar form, another form of the polar form. We talked about the argument of z last time as well. And the argument of z is simply an angle, and it's the angle that's represented specifically the angle that is between 0 and 2 pi, or 0 and 360 if we were looking at radian measure. And so if you'll come back to this one we had before, we actually had gotten an original value of 2 and 300 degrees. And it's equivalent to say that the polar coordinate could be 2 and negative 60 degrees. I mean, those are two forms of a polar, polar coordinate form for this particular point. But the argument is, by definition, the 300 value, not the negative 60. All right, so we're going to actually take a polar coordinate and we're going to write it back in rectangular form. And in order to do that, we can take this and we can recognize the pieces. This is r, and this is, of course, theta. So r is 3, and if we're taking a look then, we can distribute this out. This is 3 cosine of 210 plus 3 sine of 210, and I'm going to put the I at the end. And the reason I'm doing that is because this is x and this is y. So I can actually find out what x and y are by simplifying and reducing 3 cosine of 210 degrees, which is a unit circle value. And on the unit circle, that 210 degrees is actually square root 3 over 2. So this is 3 times this square root of 3 over 2. Remember, 210 would put us down here in quadrant 3. And then we would end up simplifying that, of course, to negative 3 square roots of 3 over 2. We do the same thing with y. Y is 3 sine of theta. I'm sorry, theta is 210 here. Let's put that in there. And so this is 3 times the sine of 210, which is negative 1/2. So this is negative 3/2. So my coordinate in rectangular form, my complex number in rectangular form, is written z equals, and you can put the z or not, but the x value, which is negative 3 square root of 3 over 2 plus yi, and y is actually negative, so we'll do negative 3/2 I. So here is my rectangular form for this complex number. Alright, so this theorem actually tells us how we combine, or two ways that we can combine complex numbers. So if you have the complex number z1, and it has r1 cosine theta 1 plus I sine theta 1, and z2 is r2 cosine theta 2 I sine theta 2. We can either multiply them together or we can divide them. when we multiply them together, what ends up happening is that the r values end up getting multiplied, right? You can see that down here. And then the angles end up being added. Okay, so that's with multiplication. When we're doing division, the r values end up getting divided. And the angles end up being subtracted. So we're going to actually do that. We have two values given to us here. We have z and we have omega, or w if you prefer. And we're asked to find z omega and z divided by omega. So we're going to find z omega first. And what this formula in the previous slide said I needed to do is I need to multiply the two r values. So this is 4 times 2. Let's try this again. 4 times 2. And then I need to write this as the cosine of the angles added. So 3 pi over 8 plus 9 pi over 16 plus I sine, and then it's 3 pi over 8 plus 9 pi over 18. All right, and of course we get 8 at the beginning of this. 2 times 4 is 8. And then in order to add these cosine values together, we need to have common denominators. So this 8 becomes a 16, and the 3 would become a 6, and then we have 6 plus 9, which gives me cosine, and 6 plus 9 is 15 pi over 16 plus I sine of 15 pi over 16. And this would be my value for z omega. We still need to do z over omega. So I'm dividing the z values, r value, which is 4, over the omega's r value, which was 2. And then I need the cosine of the two angles subtracted. So this is 3 pi over 8 minus 9 pi over 16 plus I sine of 3 pi over 8 minus 9 pi over 16. And this is 2. 4 divided by 2 is 2. And then just like on the last slide, this needs to be 16 and 6. So we end up having the cosine of 6 minus 9, which would be negative 3 over 16 pi, or 3 pi over 16. And then plus the I sine of negative 3 pi over 16. Now, cosine of a negative value is the same as cosine of the positive value because it's an even function, which we've talked about before. So this can actually just be replaced with the cosine of 3 pi over 16. Sine is an odd function, so the negative on the inside of the angle can be removed to the negative on the outside using that feature, and we have minus the sine of 3 pi over 16 when we reduce and simplify. The next thing we're looking at is actually de Moivre's theorem, which is part of the title of this section. De Moivre's theorem talks about raising values to powers, and it's going to become more helpful even when we look into the next theorem that we have. But for now, what you're noticing is the extenuation or a further example of what we just did in the last theorem. So our last theorem said that when we have two numbers multiplied, right, z1 and z2 here, we multiply the r values, and we add the angles. Well, if we multiply to the same r value a bunch of times, like r times r times r, if they all had the same r value, that would be r to a power, however many times we had that. So you see on this formula r to the power n, because it's multiplied by itself n times. And then if the angles were the same from over here, right, our angles are supposed to be added, theta 1 plus theta 2. Well, if all the thetas are the same and we add it multiple times, multiple additions is actually multiplication. And so we would multiply it by the value n. So de Moivre's theorem is just in some cases, a simplified example, right, because it's the same z value, but it is the z values multiplied by themselves, so z times z, and then we use that example, and then we multiply by z again, and we use that same theorem from before. So we're going to take an example where we have 1/2 times the cosine of 72 degrees plus I sine 72 degrees. This is all raised to the 5th power. So the first thing that we have to recognize when we're looking here is sort of this distributive kind of process, or not to forget anyway, the 1/2. So over here the formula says I need to take the r value in this case, which is 1/2, and I need to raise it to the power of n. So I need my 1/2 raised to the 5th power. And then after that, I need the cosine value, and I need my angle measurements, which is 72 degrees, to be multiplied by 5. All right, so the 1/2 to the 5th is actually 1/32. And then 72 times 5 is actually 360. So this is cosine 360 plus I sine of 360, which is, of course, values that we know something about. In particular, the cosine of 360 is 1, and the sine of 360 is actually 0. So we can represent this in one of two ways. We can either just represent this as 1/32, or if you want to be real specific of the directions, and my math lab may force this to happen, you could write this as 1/32 plus 0i, because b is actually the value of 0 in this problem. So I'm fine with the first one, but my math lab may make you do the second. All right, and our last theorem of the semester is talking about finding complex roots, and it's actually very similar to Moivre's theorem that we just looked at, but it talks about the nth root as opposed to the powers of n, being a power of n. So one of the things that you learned back when you first learned about square roots, and to give you an example, if you talk about the square root of 4, the square root of 4 actually has 2 square roots. It has the square root that's 2, or it has the square root of -2, because 2 times 2 is 4, and -2 times -2 is 4. And so it has 2 answers, and the reason it has 2 answers is because it is a square root. Now, nobody probably really emphasized that much beyond square roots for you, because it gets tricky, right? So if you take the number 8, and you wanted to do the cube root, well, the cube root of 8 in the real numbers has one and only one cube root. It's 2. 2 to the 3rd is 2. And there isn't any other number in the real number system that when you raise it to the power of 3 will equal 8. The reason, though, is because the other 2 solutions are actually in the complex number system. So we're going to take an example of this complex number system, and we're just decided not to use 8. I'm using something a little bit more general. We're going to use actually a complex number, but let's take a look at this formula and see what we're going to be doing. So you're going to be taking the nth root of whatever the r value is. You notice that you've got an angle theta 0, and it has to be divided by n. And then you've got 2k pi, which would be equivalent to 360 degrees if we were working in radians, right? So this could be written as 360 degrees times k. And k, well, we'll get there in a minute, but times the k. And we could do that for that piece, and then it's divided by, again, the same n value that you're taking the nth root of. And then your k values go from 0 up to n minus 1. So in particular, k will always start at 0. It will stop 1 shy of where you are, but if you're doing an nth root, you would have n k values, which would give you n distinctly different roots. All right, so the formula will make more sense as we do an example, so let's try one. And we're going to find the complex roots of 4 minus 4 square root of 3i. And as we take a look at that, you might sort of notice back over here on the directions that finding complex roots sort of starts with having things in polar form, and that's actually where we're going to have to start. But in order to be able to process through any of this any further, we've got to change this into polar form. So I actually need to know the r value, I need to know the theta value and whatnot, and I can think through that if I do this with triangles, and it's a good review for us as well, since we are going to be very quickly moving into a final exam that's going to have some triangles on it. So the first thing is that 4 and negative 4 square roots of 3 would put us in quadrant 4 because the x value is positive and the y value is negative. So we're going to be somewhere down here. And here's my point. I can actually make a right triangle here. In my right triangle, this x value is 4, my y value is negative 4 square root of 3, and I can find the hypotenuse, which is the z value, it's the magnitude. So my magnitude is actually found using the Pythagorean theorem, or using the formula, which is based on that, as the square root of 4 squared plus negative 4 square root of 3 quantity squared. Now when you notice this, of course, 4 squared is 16. The next thing you have to notice is that you're squaring a negative, so it is going to be positive. But you have to square both the 4 and the 3. So squaring the 4 gives me 16, and squaring the square root of 3 would give me 3. Now, if you actually multiply 16 times 3, and add 16, we're going to end up getting the square root of 64, which is, of course, 8. So z is 8. I also need the angle measurement, the theta value, and I want to show you, while this one is really nice and clean, I want to show you sort of in general what you would do to find it. In general, you can look at the relationship between the two sides, 4 and negative 4 square root of 3, which, of course, we've done before. And the relationship in a right triangle between those two sides is tangent. So the tangent of the angle that I'm looking for, or at least close to the angle I'm looking for, is the opposite, which is negative 4 square root of 3, over adjacent, which is 4, and then the 4's will reduce. So I actually have negative square root of 3 over 1, and that doesn't exactly match up to my unit circle, but we're getting close. If I represented it as negative 3 square root of 3 over 2 over 1/2, then I look like I'm on my unit circle. In particular, notice that this actually says we want to do this in degrees, so taking a look at your unit circle, you've got y over x for tangent, so you're looking for the y value to be the negative square root of 3 over 2, and the x value to be the 1/2. Likewise, you could look at this and say, oh, the square root of 3 and the 1/2, I get those, that's the 30, 60, 90 triangles, and if I were dealing with 30, 60, 90 triangles, I can go back to my picture over here, and in my picture, the opposite side of the 4 square roots of 3 is a bigger length than the side of the 4, so it has to have the bigger angle. It's the 60-degree angle. So this angle inside of here, right here, is 60 degrees. Now, that's not actually the argument, though. The argument is this angle around here, and of course that angle would have to be 300 if the angle inside was 60. So I actually have an, in my polar form, I have z equals r, which is 8, times the cosine of 300 degrees plus I sine of 300 degrees. So this is the original polar coordinate form that I have to start in order to even be able to use this theorem over here. All right, this formula, this can't be used without polar form already, so I've got to get in polar form, so that's what we did first. All right, so the kicker then is we need to take this, and I'll move it to the next slide, and we're going to use this in order to find the roots. So my formula for finding roots, and let me put part of that on here too. Let's see if I can copy that over there. No problem. And for our practical purposes, of course, the value of interest to us is the degree measure because we're working in degrees. So these are the sort of the two pieces of information we need right now. All right, so this says that I am going to let my k, oh, and the other thing was that there was a piece of information that told us what k had to be doing. K would go from 0 to 1 to 2, and it will stop at 3 here because I want to find the fourth roots, right? Fourth roots would mean that n is 4. So my k value stops just one shy of that. All right, so we've got 4 k values that we're working with. We're going to start with z sub 0, and z sub 0 would be the fourth root of 8. and then we would have the cosine of 300 degrees divided by n, and n is, in this problem, 4, so that's going to stay stationary every time. I'm going to have 300 over 4. And then I'm going to have 360 times, in this case, 0, because k is 0 on this particular rendition of my roots, divided again by 4, plus, and then we have I sine of the same values. So just so that we've got it written in properly, we'll go ahead and write them one more time. Okay, and we need a bracket out there too. Okay, so this is the 4th root of 8, and then the 300 over 4 is 75, so I have the cosine of 75, and the 360 times 0 is, of course, 0, so then I have the same angle over here, so I have cosine 75, and then I sine of 75. So we're going to use this sort of formula approach one more time before we talk about what's really happening between the different roots that we're finding. All right, so let's find z1 next. So my formula starts out the same, 4th root of 8, and it starts out the same again, cosine of the 300 divided by 4. So I'm going to actually write that as 75. It'll always be 75 because n is always 4. The difference is going to be this piece right here. This is 360, and now k value is 1 divided by my 4. And then I have I sine of the same quantities. So I sine of 75 plus 360 times 1 over 4. All right, but what is 360 divided by 4? Well, it's 90, right? So I actually take my same angle I had before, 75, and I add 90 to it. So 75 plus 90 would be 165. So I have cosine of 165 plus I sine of 165. And that's C1. But pause with me for a moment before we actually go through this process again and actually really write down another angle measure and all that. If I let k equal to 2, so I'm sort of looking at this piece right here. If I had k equal to 2 in there, and instead of having added 90, right, 360 divided by 4, I would have taken 360 times 2, which is 720, and I would have divided by 4. I would have actually ended up getting 180. So instead of adding the 75, I would have added 180 to the 75 instead of 90. Well, that's just 90 more than I did before, right? First time I added 90, and the second time I'm going to add 180, and lo and behold, if we do it again, the third time I'm going to add 270. Every time I'm adding 90 more, and if you think about it, I mean, think about a pizza. This is what you do when you slice equal slices of a pizza, is each of those angles are the same, and when you're looking at those pieces, that's what we're doing here. We've made our incision in one spot and said, here's where my pizza is going to start, and if I want 4 pieces, they have to be 90 degrees, and the central angle would have to be 90 degrees. So I can actually take this idea that we've got here, and I can add another 90 degrees to that 165 to get Z2. And almost right here, so hang on a sec. So we're going to do Z2. It's, again, the 4th root of 8. And then I'm going to have the cosine, and I want the cosine of the same angle, but 90 more. So it was 165, so now it will be 255. Plus I sine of 255. And yet again, we can go for the last one, 4th root of 8, and I add 90 degrees again to the 255, making it 345. Okay, I've got some parenthesis issues clearly. Here's what I need. There we go. Either use the parentheses or don't. You don't actually really need them. So this is actually where I need my parentheses. Let's do that. Let's fix it that way. All right, there's where we need that. So I've got a parenthesis here. And then I need to add 90 to the 255, so that's 345 plus I sine of 345. And that will be our last of our roots. So we have 4 roots. They're all at different points around the unit circle. If I were to raise any of them to the power of 4, I would get back the original polar coordinate that I started with, which is equivalent to the rectangular coordinate that I was given.